давайте начнем семинар. Я вот не знаю, будет ли руководитель вступительное слово или потом скажет. Ну вот, может быть, Ариш сама вначале, ну может, да. Как вы знаете, выступление будет на английском языке. Ну вот здесь все написано, кто выступает, откуда, я имею в виду, какую организацию представляет. И вот написано даже по какой специальности. Ну это специальность этого аспирантуры и специализация, по которой защита будет. Это наша бывшая вот эта 010315, да, или как она там, не забыл. Ну хорошо, ну давайте тогда, Ариш, пожалуйста, начинайте.
Good morning, everyone. Let me start introduce myself. I am Arij Al Adel, a PhD student at Farkateh Moscow Institute of Physics and Technology, and my research is focused on processing long-range documents using transformers. The title of my research is Transformer Modifications for Various Long Document Processing Tasks. My presentation is divided into three main parts. First part is theoretical and includes motivation and background, scientific actuality of the research, goal, tasks, scientific novelty, and theoretical and practical value of the work. The second part is dedicated to introduce the results of experiments on different structural modifications proposed in this thesis and the application on different NLP tasks such as translation, mask language modeling, question answering and summarization, and final part is a conclusion part that summarizes the work and introduces the publications submitted for the defense. Finally, we will stop with your notes and questions. Starting with the motivation and background of the work. So to understand the importance of processing long documents, so it is known that the predominant capacity of the transformer comes at the cost of quadratic computational and memory complexity concerning the length of the input, which leads to a predefined input length for the transformer-based models. And this length usually is 512 tokens. And as we know, the 512 tokens is the length that most of the pre-trained language models trained on. As a result, it's extremely difficult to leverage transformers to tackle long sequences. And this is a fatal flaw concerning that long text is a pervasive information medium, including scientific documents or meeting scripts and books, to name a few. So my work was not the first work to tackle this issue. There were many previous works, and they can be categorized into two categories. First category is dividing the long document into segments, and as an example, we have two subcategories, even hierarchical, as example hybrid, or recurrence as transformer XL. In hybrid, they have used two encoders, one encoder to encode each sentence into a vector, and the second encoder is to get the contextual embedding for each sentence and the document considering the surrounding sentences. And the transformer XL, the authors, instead of computing the previous hidden states from scratch to calculate the new representation of the next chunk, they have used it as a freezed and additional context. And in this situation, each token in the next layer have a more perceptive field of tokens. So as we can see, the last token and the layer 2 can see further token from layer to layer. The second category is processing the inputs as one chunk using sparse attention, and this is a big family including ETC, Big Bird, Long-T5, GMAT, etc. And for short, I will explain just two of them, Longformer and ETC. In Longformer attention, the authors add a global attention and made it symmetric as explained in figure T. Symmetric, this means that each global token has access to all memory, to all tokens in the long sequence, and all tokens are depending on it. Before this last proposed variant, authors used two other kind of attention, dilated and sliding, but these two kinds of attention didn't result in good outcome, model performance as using global and sliding window. The second approach is ETC, which is encoder-based model, which is a natural extension of the Longformer, but it is dedicated to processing structural input. That is, if we have a document from two paragraphs, each paragraph has two sentences, so each sentence has its own global tokens, and each paragraph has its own global tokens also. And as we can understand, using ETC requires a complicated data pre-processing. In our work, we don't need this kind of complex data pre-processing. We just chunk the input and prepend each chunk with its related memory slot, as it will be explained later. So the scientific actuality of the work, as explained in the previous slide, that the long input nowadays is very common, and we need to leverage from the transformer state of the art results in processing long inputs. And from this, the scientific actuality of the work is concluded. So the goal of this thesis mainly is to empower the transformer architecture with the techniques that enables it to consume longer. And this is by using different kind of mask mechanisms and using playing on the used positional encoding used in the transformer, and leverage from previous proposed chunk approaches. And
excuse me, please. May we ask questions on the fly?
yes.
Well, what is long? Long, well, I know what is large language models, but I don't know what is long in your context.
Yes, I have
to specify, because
yes.
maybe your long is too short.
Maybe, but for this study, I have defined that the long document is a document that is longer than 512 tokens.
Thank you. Thank you.
Welcome.
It would be better to write on slides.
It will depend on what?
It would be better to write on slides what is long.
Right, this information about what is long.
I didn't understand the last word.
Okay, continue, please.
Okay. So to achieve this goal, the following tasks were achieved. First, publications that are related into processing long documents was achieved to build the later plan for the structural modifications of the proposed solutions. And this plan was basically depending on the studying the mask patterns and the transformer to solve such kind of issues, positional encoding, and how to use additional tokens in the transformer and chunk approaches and so on. After that, step by step, the modifications were implemented and applied on different NLP tasks to understand the efficiency of each proposed design for processing longer input, and the results were published in public domain. So the scientific novelty of the work can be summarized in two main points. First point is that the proposed structural modifications of the T5 encoder-decoder architecture, which is mainly from Hugging Face, to process longer inputs than the standard input links, which, as I explained, 512 tokens. Second, an extensive investigation was conducted to evaluate the efficiency of the modifications using different NLP tasks such as translation, mask language modeling, question answering, and summarization tasks. The theoretical and practical value of the work can be summarized in the 5 points. First point is that the exploration of the proposed variants of transformer modifications for processing long input. These new modifications led to break down the attention computational barrier, that is, the complexity grows linearly with the number of input chunks, not quadratically with the input links. And this thesis presents a new usage for the internal global tokens. I call them memory tokens, and proper masking technique with proper usage for the relative positional encoding. Even the original relative positional encoding proposed by T5 or by modifying it directly and use it. The modifications resulted in finally in consuming longer range input. We will see that in summarization task, and the models trained as a part of the dissertation were publicly available. To start with the proposed model, which consists basically of three components: encoder, decoder, and chunk selector. Each component will be explained in detail in the next slides. To start with the chunking approach, first, let us suppose that we have long input. And for this long input, we want to divide it into 4 chunks dynamically. So we prepend each chunk with its memory slot. This memory slot can be 1 or more memory tokens. This is for the query. But for the key and value and the attention, we prepend each chunk with all memory slots of the chunked input. And after each encoder layer, we update the memory content in the key and value and in the query. So just to mention how the attention looks like inside the memory attention, M1 represents the memory slot 1, M2 memory slot 2, and as I said, each memory slot can contain one or more memory token. So each memory slot has access to all memory slots and the chunked input and just access into a related chunk. And this allow for memory for information compression of the chunk representation, and also from the other chunks through the memory slots. And each chunk has access to all memory slots and the tokens of the chunk itself. And this allows for the information interaction between the chunk and other chunks through the memory slots. And this is what I mean by information interchange. For the data compression, as I said here, it goes on through the access from the memory slot into the related chunk. So this is the overall imagination. For the implementation, it was implemented like this. I have separated the memory slots from the related chunk and calculated the attention for each of them separately. To understand it better, as we can see here from figure A, this is the standard design of the attention. For my design, inside the memory attention, we separate each chunk from its related memory. And as I said, I calculate the attention for each of them separately. So I calculate the attention weights separately for the memory and for the related chunk. Then to relate each memory slot with its related chunk, I'm using the original positional encoding, relative positional encoding proposed by T5. After that, after relating each memory slot with the related chunk, I separate them again to calculate the final attention value, concatenate all the representations from all head, concatenate the memory with a chunk representation, and finally apply the linear layer. This is the first design. The second design is applying the linear layer before concatenating the final representation of the memory and related chunk. The same thing is applied for applying feed-forward layer. So we have just feed-forward layer for the concatenation of the memory and the sequence or chunk after memory attention, or each of them has its own feed-forward layer. And this results with 4 design variants. Second component is selector, and its function is to calculate a score for each chunk in the input, depending on the just the compressed representation, which is memory slots, and the target tokens from the decoder. After calculating the score for each chunk, the score of each chunk is multiplied by the representation of each chunk, and the weighted representations were summed up to get the overall representation. We can consider it as a compressed representation of the long chunk, which practically is, in this example, force. The size of the overall representation is exactly as the size of one chunk. So, but let us note that we have for each token and the target separate representation, not as a traditional transformer. In a traditional transformer, we have just one hidden state coming from the encoder, and this hidden state is used to generate all the target tokens. And this is a bottleneck later for later experiments when we will increase the chunk length. But for the translation task, I didn't notice this issue. So starting with the application, the first application was on translation task, agnostic aware dataset and context aware dataset. And in the slide, there are two examples of each dataset. The first dataset is a translation from English to Russian, as we can see. The second dataset is context-aware dataset, where we have a document, and this document is chunked into with a slide of 4 sentences, and a shift 1 sentence in each example. And just as a quick explanation, as we can note that the second sentence and the first sample is the first sentence, the second sample, and so on. So on the next slide, there are the experiments set up. And as we can see from the results, as I explained, we have 4 versions of the model. And I call them, for simplicity, version 1, 2, 3, and 4. For quick explanation, version 1, we have 1 linear layer in the attention and 2 separate feed forward. So as we can see, concerning the blue value, all the versions of the proposed model overcomes the baseline T5 for context agnostic translation, especially version 3 and version 1. For context-aware translation, just a quick note that the model is resilient for the number of chunks. So the same model with any change of parameter numbers can process even 1 chunk or more than 1 chunk. So for the context-aware translation, if we train the model from scratch, we will get very bad blue score for all model versions. While if we fine-tune here in the context of translation task, by the word fine-tuning, I mean using the same retrained model from the previous slide on the context agnostic dataset on context-aware dataset. And as we can see, the results directly became much more better using the version 4 and version 1 from the model. This is for the translation task. To understand the efficiency of the proposed model for other NLP tasks, the translation task is not enough, and we need to pre-train the model from scratch on masked language modeling. And as an objective, a complete PyTorch pipeline was implemented to mask the input according to the T5 objective presented in the slide. And using these experiments setup, I have the following results. As for this group of experiments, the maximum length used was 512, and this is for the following reason. I want to understand how good the performance of the proposed model comparing to the baseline, just because all the previous works that were presented in this presentation as background didn't pass the baselines on the basic input links, 512. The benefit were when they used longer input. So on this group of experiments, I want to know the efficiency of the proposed model on the basic input links first, then move to longer inputs. As we can see from the table 4, the proposed model give us better perplexity, even we are using just one chunk with 128 links. And this, from this table, we can conclude that the memory slot has an important role for to get better chunk tokens representation that led to better model performance. In the table 5, looking into lines 1 and 3 and 5 to compare the proposed model with the baseline using chunk of 512 tokens. Comparing the line 3, we can see that the proposed model gave us better results than the baseline, and the reason as explained in the table 4. The memory slot has helped to get better representation for the chunk tokens. What about if the same input is chunked into 4 chunks? Again, the results are better than the baseline, but worse than using one chunk. And this can explain as following. The memory slots helped us to get better chunk representation, and the interaction between memory slots helped to compensate the information loss resulted from chunking. And anyway, the proposed model gave us better results than the baseline. For the line 2 and 4, they are just simply continue pre-training the models from table 4 using just longer input. And as we can see, continue pre-training with longer input doesn't result with better perplexity. So pre-training the model, even the proposed model or T5 from scratch or mask language modeling is better than continue pre-training. Is there any question here? Continue. So as I said, when I increased the chunk input, I have got a huge computational cost. So resulted from using the selector component. That is why we had to drop it, and I prefer to use the memory slots directly into encoder-decoder attention using T5 cross attention. The second modification was to use T5 cross attention instead of T5 memory attention with using a relative positional encoding in the encoder to relate the memory with the chunk. As we know, in cross attention, we don't use a relative positional encoding in the decoder. So to relate the memory with a chunk, I have added the usage of the relative positional encoding. I tried to pre-train the model again on previous task, mask language modeling. And as we can see here, that the proposed model and all its modifications resulted in better results than the baseline concerning the perplexity and value. What is interesting to note that using just a memory slot of 2 tokens just give us, using Adam optimizer, give us better results even the proposed model, original version, and the baseline T5. And this again emphasizes the memory ability to compress the chunks representation. The same note for the using add a factor. Again, better perplexity, better accuracy comparing with all models that use the add a factor. What if we use the different scheduler, constant? Using constant brings the results up, down, and the proposed model with all versions, with all modifications, were worse than the baseline. But anyway, we can note that using just the memory representation give us better results than using the complete representation of the chunks used by the proposed model. And this again emphasizes the compression ability of the memory slots that need to be investigated in the future. Anyway, as we know that the results of mask language modeling task doesn't show us and present the results on downstream tasks such as translation or question answering or summarization. So if I have a superior model on mask language model, this doesn't mean that I will have superior results on the downstream tasks. So I have tried to investigate the model performance on question answering task using hotbot QA, and in the slide a sample from this data set in which we can see a question and answer and a context. Context is from 10 paragraphs, and each paragraph is a long paragraph. For application, I have concatenated the question with the context as one input to be chunked later, and I will predict the answer. As a result, using the linear scheduler, unfortunately, both the baseline and the proposed models were not able to tackle the task, while using the constant, the same tendency was noticed where the baseline was better than the proposed model with all versions. As we can see, the same tendency was about using the memory as a compressed representation for the chunks, which emphasize the role of memory slots of data compression. From this group of experiments, I have three conclusions. First, the memory slots have a compression property that needs more investigation in the future. The second, the memory slots have an important role for information interflow between the input chunks. Second, the pre-training stage is very computationally expensive, and I need a solution to solve this issue. These three notes lead me to the final design to just avoid the expensive pre-training stage. And for the design, I have prevented the memory slot from attending to all memory slots, just to emphasize the compression ability of the memory slot. Also, I kept the access from the tokens of the chunk to all memory slots. And I have modified, this is concerning the masking and access. For the relative positional encoding, I have modified it in the following case. The relative positional encoding applied into between tokens of each chunk is as original as in the T5, while I have computed the relative positional encoding between memory slots as following. Each token in each memory slot has the same positional encoding. So the memory slot 1, which consists of 2 memory slots, each memory slot has a position 0. And for the tokens of the second memory slot, they have the position 1 and so on. So the position encoding between memory slots was computed like here. The memory, we need also to compute the positional encoding between the memory and related chunk. So 0 is the memory token, the position of memory tokens, and as usual, just the distance between the tokens of the chunks and the memory. Also, I need to compute this, but I need to mask it anyway. So this is, I have elevated it in the implementation. So I need to use these for kind of computation. So I can, as a pre-trained weights, I can leverage from just this from T5, while during fine-tuning, I'm initializing these weights needed for the positional encoding from scratch. The application was for summarization task using just 3 data sets, SumSum, GovReport, and CNN. And these data sets are from normal input into long input in GovReport, as explained in table 10. We have the statistics that present the number of samples in each data set, and the lengths of input and the summary, mean and median and max. And in the table 11, we have the links that is used for experiments. And with no limit, I mean that I have consumed all the input links. For experiments, I have used as input document by document to emulate the human approach of reading. We read document by document, not 10 documents by 10 documents. And for comparison, I need another model that use the same tokenizer. I need this step just because I need to compare these models to understand the structural modifications. So I need the same tokenizer, the same pre-trained weights, etc., etc. Another works can compare between encoder-decoder, between encoder and decoder models, and I don't want to compare this. I just want to compare the structural modifications, and this is the reason behind using these models. So SLED model practically is similar to my model, but it doesn't use the memory slots. It's just chunking the input, and in the decoder, after chunking, it concatenate all these chunks using the techniques fusion in the decoder, and that's it. There is no memory usage in this model, and the T5 base model and my model. So I have tried to use a chunk of 256 and increased the chunk length. And I have tried to use also a different memory slot size. So as we can note from this table, that varying the input, the memory slot size didn't result in how to say it, didn't result in a clear tendency of results improvement. So sometimes using 8 memory tokens result in better results, sometimes using 16. So depending on, so we didn't have a clear result from changing the memory size. But with increasing the chunk size, we got better results. And we can note that the proposed model results with better results comparing with the SLED as a baseline and a T5 as a baseline. So the proposed model resulted in better results. For the CNN and Daily Mail, results presented in the table 13 was just for the epoch 6, not for the epoch 10s, because I forgot to say that all experiments were for 10 epochs, for 2 times, average for 2 times. And for the results of CNN and Gov report, the baseline resulted in better results with a small difference between the T5 and the proposed model, while the proposed model and the baseline T5 were much more better than the SLED. What is the result of that? As I said, practically SLED somehow close to my model, but they don't use memory or global tokens for the chunks, and my model using the memory slots. And this emphasizes the importance of memory slots for information interaction, and as I said from the previous tasks, the small difference between the proposed model and the T5 baseline emphasize also of the importance of memory slots. But what is the difference? Okay, using chunking in the proposed model give us less computational cost. This is the results. So the comparable results here emphasize the efficiency of the proposed model. Finally, with the publications submitted for the defense, there are 3 publications. First publication was dedicated for the first modifications applied into translation task. Second publication was dedicated into the second group of modifications and their applications on mask language modeling and question answering task. And the third application was dedicated for the final group of modification dedicated on the changing masking and relative positional encoding used in the proposed model, and application on summarization task. In the conclusion, the following theoretical and practical outcomes of overall model modifications development stages are a review of proposed models for processing documents for different NLP tasks was achieved with a review also of all proposed model modifications on different NLP tasks and applications on them, and a new usage for global tokens as a memory slot to relate chunked inputs as a compressed representation. And finally, the developed designs were implemented, and the results were publicly published on the internet. That's it for the presentations, and I'm ready for questions and notes.
That's all. Thank you very much. Я думаю, может быть, вопросы можно по-русски задавать, да?
Да, можно.
Да. Вот из аудитории есть вопрос какой-нибудь? А вот вы подойдите тогда сюда. Ну, вы да. Сейчас, девушка, спросите.
Я не вижу. Как мне смотреть?
Нет, это нормально все. Сейчас. Вопрос зададут сейчас.
Давай.
For your presentation, and I saw the results. And with which length of sequences the results were obtained? Because you know that it has an imply on runtime and memory. Well, the length of the sequences. It was the last slide with the results. I just asked for
This one?
Yep. You know that self-attention operation in transformer-based models scales
Quadratic with that.
With the growth of sequence length, and so.
What is the question?
Which length of sequences was while you were obtaining these results?
Again, what? Again.
Length of sequences you have.
As
Test.
okay, the length. Okay, the length of sequences is introduced in table 11 for experiment. So for the Gov report, I have maximum input length 3078. But as I said, the input is chunked, even for 256 for each chunk, or 348 for each chunk. Usually for the last chunk of the input, maybe it will be less than, so it's embedded just.
Thank you.
Okay.
Okay. Thank you.
Okay.
Any questions? Николай Вячеславович, пожалуйста.
Thank you very much for your talk, indeed. Did you have any mathematical challenge in your research?
Actually, not just because my research is not about mathematics in general, it's about just structural modification. So I had just to represent the equations of the attention. That is, and it was easy. It was simple, not that.
Thank you.
Welcome.
Ариш, я хотел сказать, почему вас спрашивают про математические результаты. У вас несколько раз в автореферате встречается фраза, а далее мы описываем математическую модель. хотя вы говорите, что вы математикой не занимаетесь. Ну, как-то так немножко противоречие есть.
Да, совершенно верно, совершенно верно. При описании модели могли быть как раз какие-то, ну, не глобальные вызовы, но какие-то изюминки, да.
Yeah, yes, I understand. Thank you for your question. I understand that, but in my case, in my study, I didn't directed my study on mathematical analysis. It was just about the results of the proposed structural modification. So here, the practical results were needed more than mathematical analysis. Questions?
Если можно, я еще немножко добавлю к
Да,
последнему вопросу.
извините, пожалуйста, Валентин, да? Может быть, вы как-то скажете, а потом, может, еще вопросы пойдут, чтобы мы как-то ориентировались.
Давайте я сначала адресуюсь к предыдущему вопросу. Я просто хотел сказать, что работа, она по информатике, а информатика – это часть математики, поэтому математические модели просто неизбежны. При этом получение новых математических результатов действительно, ну, как сказать, мы его здесь не ожидаем. Это работа скорее именно технического плана, и я лично не вижу в этом какого-то недостатка для работы, просто она направлена на другое. Вот, относительно того, что можно сказать про работу, я хотел, наверное, подчеркнуть самое важное, что выбрана достаточно интересная узкая задача про длинные контексты, с одной стороны. С другой стороны, хотел бы подчеркнуть то, что Ариш все исследования выполнила исключительно сама, и все результаты получены исключительно ей самостоятельно. То есть это работа, выполненная фактически одним человеком, что, на мой взгляд, только увеличивает ее ценность.
Так, да, пожалуйста. Ну, вот подойдите, чтобы слышно было хорошо.
Hello, thank you for your presentation. I have a little remark. You have shown us a slide with example of translation. Could you show it again, please?
What should?
Translation of sentences.
This one?
No, I mean example of Russian English. Yeah. So there is some grammatical mistakes.
Yes, I understand you. I just want to explain that I didn't how to say implement or has any kind of contribution to this data set. This data set was ready to use, and I got it from a work of Yelena Voita. Yelena Voita has a work on translation task with context-aware and context-agnostic translation. And I have got this translation from her publication. So this, I didn't write the examples in this data set. So, and it's normal if there is any kind of grammatical mistakes, because in any data set used for machine or fine-tuning or training, all of them have some mistakes. This is normal.
Okay, thank you. And on the slide 27, as I remember,
27.
You show us training for 100 epochs. Isn't the model overfitted?
No. We don't have overfitting.
Okay. So thank you.
Welcome.
Okay. Так.
I have some question, Юрий Алексеевич.
Я. Это кто у нас тут?
Иван Бондаренко.
Иван появился. Хорошо.
Yes, yeah.
Arij, hello. Thank you for your speech, for your interesting speech. And I have a small question. As I know, there are different approaches to solving long sequence problems. For example, recurrent architectures such as recurrent memory transformer or Mamba architecture and so on. Do you compare your approach with other methods to solve the long sequence problem in transformers?
Thanks for your question. This is a very important question. Actually, in the current studies, there were no comparison with any previous works that worked with memory or global tokens, if this is a question. If your question's about a comparison with other models that work with long documents, then yes, I have a comparison with the SLED. SLED is a model that is dedicated for processing long documents. Does that answer your question?
Okay, thank you. Thank you.
Welcome.
Ой, извините, я по-русски хочу спросить.
Да.
Вот вы сравниваете вот с базовой моделью и еще с какой-то одной слайд, да, которая моделью, и свои результаты сравниваете, результат тех моделей и других. А вообще, какое положение в мире? Вот на самом деле, я думаю, что никого не удовлетворяют результаты точности и полноты, да, или там F-меры. Какие лучшие достижения в обработке документов? Какие достигаются показатели точности, полноты? Можете сказать?
Yes, I have said that when we are when we use long inputs, it is very computationally expensive, using hardware resources and time also. But using chunk approach, as I explained during the presentation, allows the model to use less resources, hardware resources, and get comparable results, as we can see. So the resource that is T5 base is consuming the long input as it is, while T5 mem base is chunking the input. And as I explained before, that the computational cost is growing linearly with the number of chunks, not quadratically with the input links, as in T5 base. Does that answer your question?
Yeah. Спасибо.
Welcome.
May I have a question?
Yes.
My name is Yelena.
Hi, Elena.
Yeah. So first of all, thank you a lot for your report, and I really appreciate your work. And my question is about, does your modification affect the model performance in terms of speed, or maybe it requires less or more steps or epochs to achieve the results?
Okay. For the comparison, I have used the same training epoch for all models. For the time, sometimes my model consumes more time, but the benefit is about using less hardware or resources.
Mm-hmm.
So this is kind of trade-off here.
I see. And don't you have any table with comparisons?
Yes, you can refer into the final publication. There is analysis and appendix to the paper. You can refer it into it.
Mm-hmm. Okay, I see. And could you show the slide number 22?
22.
Mm-hmm. Yeah, probably I missed the table number 5. Why the experiment number 4 achieves so bad results? Maybe you have some intuition.
I want for these experiments line 2 and 4 to understand if for better sound I advise to close our so to listen to me.
Yeah.
For line 2 and 4, I wanted to understand the consequences of continuing pre-training, but using longer input links. And practically, the practical result is worse than pre-training from scratch. Yes, so this is a practical result, and I don't have explanation to it. If you have, I will be happy because I searched about it, and there's some works, to be honest with you, some works mentioned that gradually increasing the input links during training and pre-training of the transformer result in better results. But practically, I didn't get this result. So we can conclude from this, don't believe everything written in the publications.
Okay, I see. Thank you a lot of. And also I have some minor notes. So could you switch to slide 6?
Slide 6.
Yeah, with the goal. So just my opinion, I think it's better to these parts, like first of all you have to study and then to suggest your own.
Again, I didn't understand your note.
In my opinion, I think it is better to switch these parts, like to first of all you have to study and then to suggest your own modification.
Study, then suggest. Okay, understand.
Yeah, and the last minor notes.
Yes.
That probably it's better to define all some terms in the beginning of the report as yeah, because not everyone who is listening to you is a specialist in NLP or even in machine learning. So probably the main terms should be defined before your presentation.
Main terms such as long input and what other term?
Probably about positional encodings and so on.
Positional encoding.
So I think you can look at your work and just highlight some more important terms.
Okay, if I will explain just a small note. It's supposed that who will listen to this presentation have a primitive understanding of some deep learning principles. What concerning the positional encoding, there are hundreds of positional encoding types, And if I will explain every type, it will take a very long time, and I have limited time. So I just have explained during the presentation the main principles of the relative positional encoding, and that is related, especially my work here. I can show you. So I thought I have explained just what is required, minimal requirements to understand the work in this part, figure 17.
I see your explanation are quite nice, and they're enough, but probably there are some terms that should be defined in advance. I can't tell you exact terms now, but probably you'll find some of them.
I will be grateful if you suggest.
Okay, that's all. And a lot of.
Ну что, наверное, мы уже замучили докладчика вопросами. Может быть, есть еще вопросы?
Да, можете задавать, давайте.
Ну да, вам уже пошли предложения о том, как улучшить презентацию или там автореферат. А у вас полный текст уже есть диссертации?
Да.
Имеется, да?
Но пока на сайте МФТИ не публиковано пока.
Ну да, это нужно решение совета, чтобы опубликовать. И так далее. Ага. Хорошо. Потому что из автореферата, ну вот...
Автореферат есть, отправить вам?
Не, ну вы-то отправляли, да. Ну там на самом деле не все понятно. Может быть.
А если есть замечания, я буду благодарна по поводу автореферата.
Нет, он просто краткое содержание там, поэтому какие-то вопросы. Я хочу вас, я не знаю, правда, как в МФТИ, вот про совет диссертационный, где вы будете защищаться, да? А вот вы у нас здесь выступаете, считаете, что мы разбираемся в моделях нейронных, моделях больших языковых моделях, трансформерах. Вообще, когда вы будете выступать перед советом, там, возможно, только треть совета в этой теме как бы обладают компетенциями. Поэтому вам придется немножко какой-то ликбез провести, да, что такое Т5 модель, Т5 модель. Еще что-то надо будет как бы про это сказать немножко. Ну, про трансформер там в введении, да, говорили, но вообще как-то вот, чтобы как-то народ почувствовал, увидел ваш вклад в эту отрасль знаний. Ну, вот это, конечно, я хочу предупредить, чтобы это как бы... Либо вы должны иметь после thank you или там после спасибо слайда еще несколько слайдов, которые поясняют такие моменты. Так обычно делают, знаете, да? Ну, слайд у вас 36 там, а еще будет 37, 38, которые вот поясняют какие-то модели, о которых вы будете упоминать, но на рассказ о которых мало времени у вас будет совсем. Ну, вот я как бы такие советы.
Да, thanks very much. Спасибо.
Ну да, вот у нас как-то ваша работа вызвала большой интерес. У нас здесь в аудитории присутствует там человек 20, еще вот в онлайн. Больше...
Могу сказать, я пока не смотрела, кто.
Так что это самое. Да, вы тут. Хорошо, ну ладно, мы тогда будем заканчивать. Большое спасибо. Желаем вам
всем
удачи, успехов, успешной защиты. Ну и вы потом напишите, чего вы от нас хотите, да, какой фидбэк,
да, конечно.
В какой форме и так далее. Ну ладно, всего тогда, всего доброго.
Иван, спасибо всем большое.
Подождите, можно еще?
Да, можно.
А вы не хотите выступить у нас более развернуто в Иннополисе?
Еще более.
Да, нет, извините, это типичное сейчас было выступление перед защитой диссертации, 40 минут, так что это не в счет, а именно полноценный доклад на семинаре в Иннополисе. До нас и доехать можно.
Это Казань.
Это далеко от меня.
Это 777 километров от Москвы. Это всего лишь 11 часов поездом и 1,5 часа самолетом.
Николай Владиславович, а онлайн вы не хотите, да?
Конечно, нет.
Ладно.
Мы подумаем. Спасибо большое. Спасибо за предложение.
Да. Угу. До свидания. Спасибо.
Да, всего доброго.
Да, до свидания. До свидания, Валентин. До свидания, Ариш. Спасибо всем, кто принял участие в дискуссии. До свидания.
До свидания.